All right, everyone, we had some homework assigned on Wednesday due today. It's worksheet number 12. It all involved these charges in external magnetic fields that we were analyzing the path of. So in essence, we can use that equation that we learned over a week ago, F is equal to QVB, because we have a charged particle in a magnetic field. But we can also use FC is equal to F is equal to mv squared over r, because that charged particle is moving in a circle and experiences centripetal force. But we can also use FC equals Fm, or mv squared over r equals qvb, because the centripetal force is caused by the magnetic force. We had 5 questions on that worksheet, worksheet number 12. The answers are up here right now for the first 3 questions. Have a look. Let me know if there's any trouble with those first 3 questions, and we'll show you the last 2, and then we'll go over the questions that we need to go over. Questions 4 and 5. Actually, we'll just put up question 4 because you can see the answer to question number 5 actually got cut off in the copy here. So just have a look at question number 4. We're going to go over question number 5 anyways, whether you think you got it right or not. Any issues with any of those questions, guys? Yep. How do you convert joules to electron volts? Okay. That was question number 4. Okay, we'll take a look at that. Same question. And we'll do number 5 for sure, because I know that some people are going to have had some trouble with number 5. Okay, number 2 and 3. Okay. Anybody for number 1? All right, we'll take a peek at 2, 3, 4, and 5 here. 2 says, how fast must an electron be traveling through a magnetic field of this strength to follow a circular path of that radius? Assuming it's traveling perpendicular to the magnetic field, which of course, we can't solve this problem if it's not traveling perpendicular to the magnetic field. It should really say that in the question. On a test or an exam, it would say that it was perpendicular. In the end, we're going to make that assumption here. If we make that assumption, we know that there's 3 equations that we're allowed to use. F is equal to QVB. We're allowed to use FC is equal to mv squared over r. And then, of course, we're allowed to use the combination of those 2 equations. FC is equal to Fm. 95% of the time, when you're dealing with a radius in the context of one of these charged particles in a magnetic field, 95% of the time, which one do you think you should go with? Which one is the one that works for us 95% of the time if we're dealing with a radius? It's the combination of the 2, right? It's FC is equal to Fm. Now, it doesn't mean for sure that it's going to work for us. But if it works 95% of the time, let's at least try that first. Okay, don't try the one that works 5% of the time. That doesn't make any sense. Okay, try the one that works the most often. mv squared over r equals qvb. Now we know that one of the v's cancels on each side, leaves us with mv over r equals q times b. Now we're looking for speed here. So we've got to take the r up by multiplying. It becomes mv equals qbr. And then we've got to take the m down by dividing. So v is equal to qbr over m. Now we're dealing with an electron, so we know the charge is 1.6 times 10 to the minus 19. The magnetic field strength is given to us. And the radius is given to us as well, 6.5 times 10 to the minus 2. We divide that all by the mass of the electron, which is on our data sheet. And we solve for the speed there. And we end up getting 3.4 times 10 to the 7th meters per second. Is that a reasonable speed for an electron? Is that reasonable? It's a little quicker than we might expect. Usually we're in that range of 10 to the 5, 10 to the 6 meters per second. But it's entirely reasonable. It's not one that you look at and say, oh, I must be wrong. Right? If you got 3.4 times 10 to the 8, that's one that you look at and say, I must be wrong, because the max speed that you can reach is 3.0 times 10 to the 8 meters per second. Okay, this is fast. It's probably faster than normal, but it's still within the range, the upper end of normal. It's not anything we should question at all. Okay, 3. What's the magnetic field strength required to make a proton with this speed follow a circular path of this radius? Once again, we're dealing with a charged particle in a magnetic field. Once again, it talks about a radius here. Once again, let's try the equation that works 95% of the time. Fc is equal to Fm. If it doesn't end up working for us because we have 2 or 3 unknowns in that equation, that's okay. No need to worry. Just go back and try one of the other 2 equations that we're allowed to use there. So Fc is mv squared over r. Fm is qvb. Okay, we cancel out one of the V's. This time we're solving for B. So we got to get rid of the Q by doing what? The Q is attached to the B by multiplying. We got to get rid of it, take it to the other side by the opposite of multiplying is dividing, right? So it's going to be B, the magnetic field is equal to mv over Q times R. Now, this is a proton. So we're going to say its mass is 1.67 times 10 to the minus 27 times the speed, which is given to us, 5 times 10 to the 5, divided by the charge of 1.6 times 10 to the minus 19. Still the same charge as an electron, right? Just positive. And R is 2.0 times 10 to the minus 2. So this equation, we say it works 95% of the time in this scenario. It works for us this time too. Let's pull out the calculator and solve this one, though, just to make sure that we can do it correctly. I still see people entering scientific notation in the way that I don't like people entering scientific notation. Okay, when I'm entering 1.6 times 10 to the minus 19, don't do this. Hey, honestly, that'll work for you most times, but I don't like it when you do that because it doesn't work for you every time. If you do that on the top up here, it will work for you every time. If you do it on the bottom, it will work for you every time if you be careful with brackets. Okay, but if you don't be careful with brackets, then it's not going to work out for you. So let's just avoid doing it this way. Let's enter it this way. 1.6, second function, EE, neg 19. Okay, that works for you every time. Okay, every time. You don't have to worry so much about brackets. There's still times when you got to use brackets, but not because of that. All right, so let's get a number on the top here. 1.67 times 10 to the minus 27. 5 times 10 to the 5. Let's press equals. And let's divide that by what's ever on the bottom here. 1.6 10 to the negative 19 times 2 times 10 to the negative 2. And when we do that math, it works out to be 0.26. And what are the units for that? What are the units for magnetic field? Yep, Tesla, good. 0.26 T. 4, what's the kinetic energy in joules and electron volts of an alpha particle that's moving this through this magnetic field follows this circular path? A little bit of a different question because usually we're asked to solve for speed. This time we're not asked to solve for kinetic energy. But look, if we can get speed, it's pretty easy to get kinetic energy, right? Ek is equal to 1/2 mv squared. So let's get speed. Let's get speed the way that we usually do in these questions by setting Fc equal to Fm. Now, be careful. Okay, all of the questions on this page use Fc is equal to Fm. That doesn't mean every question down the road, like you saw for in worksheet number 11, you're going to say Fc equals Fm. Okay, we're using Fc equals Fm for each of these questions because we've got a radius, or we're looking for a radius. If you don't have that radius, you're probably not going to use that combined equation. It's probably just going to be F is equal to QVB. But in the end, they're all valid. So in the end, if you try this every single time, even when you don't have a radius, it's not going to get you the wrong answer. You just have to try something else. All right, so mv squared over r equals QVB. V's cancel. V ends up being equal to QBR. The r goes up by multiplying, divided by m. So let's get the speed. Hey, we multiply those things together, do the math there. When we get the speed, it works out to be 120,300.75 meters per second. 1.2 times 10 to the 5 meters per second. Okay, perfectly reasonable speed. Probably didn't make a mistake here because we got in that 10 to the 5 meters per second range. Let's calculate the kinetic energy though. Say Ek is equal to 1/2 mv squared. Okay, it's an alpha particle, so let's use the mass of the alpha particle. Let's use the speed we just got. When we do that, we get 4.8 times 10 to the minus 17 joules. And I can see here on my answer key, actually, that I forgot to convert that to electron volts myself. So the question from, I think it was Bo, yeah, how do we convert that to electron volts? Let's do that now. Okay, I'm doing this for the first time myself as well because it's not on my answer key there. Remember that 1 electron volt is equal to 1.6 times 10 to the minus 19. And we're told that on our data sheet. If you look on your data sheet, 1 electron volt equals 1.6 times 10 to the minus 19 joules. So let's set those equal to each other, but in the form of a fraction here. 1.1 equals, or 1 over 1.6. Well, that equals x over 4.8 times 10 to the minus 17 joules. So if 1 is equal to 1.6, then x is equal to 4.8. Let's take the 4.8 up by multiplying. That means to solve for x, the electron volts, we end up dividing 4.8 times 10 to the minus 17 by 1.6 times 10 to the minus 19. And I think that's going to work out to be 3.0 times 10 to the 2. Is that right? So 300 electron volts it would be. All right? It's been a little while since we've dealt with electron volts, right? Because that was an electricity unit, like a unit for energy, but in our electricity section, electricity chapter of the year here. So it's funny how some of these things, though, kind of rear their ugly head again, right? Some of the stuff like, let's say, elastic collisions. Well, you tend not to see again until your final exam. But then there's certain things that do rear their ugly heads again every once in a while throughout the course. All right, question number 5. That's what I thought to be the challenging question here. Let's take a look at that one now. How does the radius of curvature of an electron's path compare to the radius of curvature of an alpha particle's path moves through the same magnetic field at the same speed? The word compare is the big word there. You want to compare two things, what do? Let's compare my age to your age. Caitlin, how old are you? 17. Well, I'm 34. Perfect. Not really, but we'll pretend I am here because the math is easier if we say that I'm 34. Let's compare my age to your age, Caitlin. How old am I compared to you? Twice as old. How'd you get that? Perfect. 34 divided by 17 is 2. So you divided those two numbers. You want to compare two things? We divide them. You could say that I'm 17 years older than you, but that's not the greatest comparison because if you compare two people, a 1-year-old and an 18-year-old, there's still a difference of 17 years, right? Well, the difference between a 1-year-old and an 18-year-old isn't the same as the difference between a 17 and a 34-year-old, and it's not the same difference as, an 80-year-old and a 97-year-old, right? So it's better to compare by dividing. We get a ratio that way, and that's a better comparison. A ratio is a better comparison than a difference between the two. So let's find a ratio here to compare. Let's say the radius of the electron's path to the radius of the alpha particle's path. Well, if we go back to it doesn't look like we solved for radius in any of these, actually. If we go back to our equation, Fc is equal to Fm, and then we rearrange that to solve for R, we end up getting for the ratio of the electron, mv, is it mv over qb? Yeah, mv over qb for the electron. And for the alpha particle, we get mv over qb. Well, we're talking about two things moving at the same speed, so v's cancel, right? mv over qb divided by mv over qb, v's cancel. Same magnetic field, b's cancel. Now all we're left with is the mass of the the mass of the electron divided by the charge of the electron divided by the mass of the alpha particle divided by the charge of the alpha particle. So let's put these two numbers in. Get a number on the top for the ratio of mass to charge of the electron. And now let's calculate m over q for the alpha particle. Get a number for that. And then once we have a number for the two of those, let's divide them. Let's do that now as a group on the calculator here. The mass of the electron, 9.11 times 10 to the minus 31. divided by the charge of the electron, 1.6 times 10 to the minus 19. Let's get a number for that. So it's 5.69 times 10 to the negative 12 for the green number there. Okay, the mass and the charge of the electron. Let's divide that by, let's use some brackets here because we're dividing by a fraction. The mass of the alpha particle, 1.67 times 10 to the minus 27 on your data sheet, divided by the charge of the alpha particle, 3.2 times 10 to the minus 19. We get a number, 0.00109. So what's the ratio? Well, Caitlin said, if we were comparing my age to her age, we divide the two. 34 divided by 17 gives me 2, so the ratio would be 2 to 1, right? Well, here the ratio would be, you could say it's 0.00109 to 1. Now, it's kind of a little bit harder of a number to kind of visualize than the 2 to 1 ratio of my age to Caitlin's age. Caitlin, if we asked for the ratio of your age to my age, what would you do? You'd divide the opposite. Good. So instead of 34 divided by 17, it would be 17 divided by 34. You get 0.5. So the ratio would be 0.5 to 1. Right? Now, you could translate that into 1 to 2, right? And that probably makes a little bit more sense for us. It's harder to do that for this number, right? Because 0.5 translated to 1, just double it, right? This one's a little bit harder there. You could do it, but we don't need to, so we won't bother. Any questions about that or any of the other questions there? All right, let's spend a few minutes talking about what we talked about on Wednesday before you did your activity. We talked about electric current. We defined it as the rate of flow of electric charge. We used an analogy of standing on the side of the highway. There's two people standing on the side of the highway. There's Devin with a radar gun. He's measuring the speed of the cars as they go by. There's Emma with a stopwatch. She's counting the number of cars that go by as she times it. She's counting the number of cars per second. Who's measuring what's analogous to current? Emma or Devin? Devin, who's measuring the speed with a radar gun. Emma, who's counting the number of cars that are going by per second. It's Emma, right? Electric current is not how fast the electrons are moving. Electric current is how many electrons or how many coulombs are traveling by a certain point per second. So it's the amount of charge per second. We can write that in coulombs per second, or as somebody mentioned on Wednesday, we can use the unit, the ampere. Sometimes we shorten that as an amp. Sometimes we shorten it even further and just call it an A. Now, in all likelihood, you're not going to get a question on an exam that just asks you to find electric current using this equation I is equal to Q over T. In all likelihood, when you see this, if you do, it'll be part of a larger question. But you know what? Before we go on to the larger questions involving electric current, let's take a look at one quick example just using this equation. So let's calculate the current in a wire which 20 coulombs of charge passes in 4 seconds. Look, we want to find current. We've got the charge. We've got the time. It's simply going to be 20.0 coulombs divided by 4.0 seconds. Easy enough, right? 20 divided by 4 is 5.00, 3 significant digits. And the units would be either coulombs per second. It's fine to leave it like that, by the way. But what's the other set of units that we usually end up writing for current? Coulombs per second, or an amp. Good, 5.0 amps. Easy enough, right? All right, easy enough. I think that I don't think we need to do any practice questions on that specifically. I think if you run into a problem where you have charge and time, I think as long as you recognize that's the equation you use, I think it becomes a pretty simple physics 20 or even science 10 problem, right? Now what we got to focus on is where this comes into play for us. Okay, we just talked about electric current. You would think we should have talked about that in the last unit when we analyzed electricity. But electricity unit, we focused on static electricity. Now we're focusing on magnetism, but in magnetism, there's a relationship between moving charges, i.e. electric current, and the magnetic force. So now we got to talk about electric current. If a charged particle moving through a magnetic field experiences a force, and they do, we know they do. We've spent time on that over the last week and a half, looking at the force on electrons and alpha particles and other charged particles as they move through an external magnetic field. If a charged particle moving through a magnetic field experiences a force, then it's going to experience that force whether it's moving through the air or moving through a wire. So let's say now we're taking an electron which was moving to the right through the air, and now we're putting it inside a wire. Now the electron is moving to the right through the wire. But we don't just have one of them. We got a whole bunch of them moving to the right through the wire. That's an electric current. Well, each one of those electrons will experience a magnetic force equal to QVB. All of them. And each one of those will want to move in a circle through that magnetic field. But they can't. This time, they can't move in a circle because they're inside the wire. So what do? Instead of moving individually down through this magnetic field, or perpendicular to this magnetic field, they drag the wire with it. So let's say we got this magnetic field that's into the page. Okay, thumb, fingers, palm, the electrons are all directed downwards, and they want to all move in a circle like this. But as I said, they can't all move in a circle like that. In fact, none of them can because the wire prevents them from moving in the circle. So they kind of get mad at the wire. Hey, we want to go in a circle. So they drag the wire down with them. They say, if I'm going down, then you're coming down with me. There is not only a force on the individual electrons, there is a force on the wire itself. The force on the wire itself, the direction of that force is in the same direction as the force on the individual electrons. So in other words, we're going to use the hand rule for deflection again. It's the exact same hand rule that we learned as our second hand rule. Thumb in the direction that the particle is moving, fingers in the direction of the magnetic field, palm will point in the direction of the force. It's no different, except that this time the electrons aren't moving through air, the electrons are moving through a wire. So it's going to still be, though, stick your thumb into the board here, fingers go in the direction of the external field from north to south, palm's going to point upwards. The force on the individual electrons would be upwards toward the top of the page. The force on the wire itself would be upwards toward the top of the page. Only difference here is the electrons, if they were individual, not within the wire, they would go in a circle. The electrons that are inside the wire can't go in a circle, so the wire doesn't go in a circle either. It just experiences that upward force. How are we going to find the magnitude of the force? This is a little bit different. It's not crazy hard. It's no harder, in fact, than finding the force on an individual electron. Right, Maddie? But it is a different equation. Instead of F is equal to QVB, which technically still applies, because there is a force on the individual electrons. It's just that we're not usually trying to find that when the electrons are inside the wire. Instead of using that equation, we're normally going to use this equation. F is equal to ILB. I stands for the electric current. And sometimes we may need to find I by using Q over T. Sometimes. So it may be a two-step problem occasionally. B stands for the magnetic field strength, the external magnetic field strength. And that's, of course, going to be measured in Tesla. What do you think L stands for? I have it listed as a lowercase l right here. That's the way they list it on your data sheet. Okay, when I write it out by hand, I usually make it an uppercase L, just so that you don't get it mixed up, confuse it as a 1. Doesn't really matter whether it's lowercase or uppercase, though. What do you think L stands for? Fraser. Okay. Yep. The length of the wire. But it's not just any random length of wire. It's the length of the wire that's in the magnetic field, or the length of the wire that's exposed to the magnetic field. So if you have a 2 meter long wire, but only a half a meter it is in the magnetic field, then you're going to use the length of not 2 meters, but 0.5 meters. What's this little thing right here? A little upside down T? Perpendicular. Just like the charged particles moving through the magnetic field, in order for the analysis that we did to be applicable, they had to be moving perpendicular to the magnetic field. The wire has to be perpendicular to the magnetic field here. So same deal. One example, and that'll be it for this topic here. It says an 8.5 centimeter length of conducting wire. We're going to circle that because we want to be in meters, right? We always want to be in meters. Lies perpendicular, that's good, perpendicular. Everything that we've learned applies because the wire is perpendicular to the external magnetic field. The magnetic field is 4.2 millitesla. We want to circle that as well because we want to be in Tesla. Current is 2.10 amps. What's the magnitude and the direction of the magnetic force on the wire? Well, we can find the magnitude by saying ILB. The current is 2.10 amps. The length of the wire is 0.0850 meters, right? 8.5 centimeters. And the magnetic field is 4.20 times 10 to the minus 3. Okay, if you don't remember what a milli is, then check your data sheet because it tells you it's 10 to the minus 3. We end up getting 7.4, works out to be 7.50 actually. 7.50 times 10 to the negative 4 newtons. Fraser? It's just the part that's exposed to the magnetic field. Now, the reality is we're looking for the strength of the magnetic force on that section of the wire. Okay, this section would actually experience a magnetic force as well because there is a magnetic field there. It's exposed to the magnetic field as well. It's just that we're looking for the force on this part of the wire. This actually wouldn't experience any force. The force on that middle part right here that we're circling in green here right now wouldn't experience a force. How come? Yeah, it's in fact, it would be pretty much parallel to the field, right? So it wouldn't be a force there. If it's at some funny angle, there'd be a force, but it's in between 0 newtons and whatever ILB works out to be. Okay. All right, we're going to have you work on these 2 questions, but we're going to have you work on them for homework. I know that you've got an assignment due tomorrow, but you've also had, 6 days to do the assignment? And these are only 2 quick questions, and I think they're going to go pretty quickly for you.